Hi guys, welcome back to the channel. In this video I will cover the enthalpy change and the calorimetry topic, which comes under energetics in the A-level chemistry curriculum. Let's begin. Okay, so starting with the enthalpy change. So the enthalpy change, the definition for it is the heat energy change which is measured at constant pressure. So this is the symbol for enthalpy change, so delta H, and the units for enthalpy change is kilojoules per moles. So it's the heat energy change which is measured at constant pressure. So remembering from GCSE, we have the exothermic reaction. So this is where the heat energy is released from the system to the surroundings. So the heat energy is given out from the system to the surroundings. And this happens when we make bonds. So when we make new bonds, the energy is released to the surroundings. And therefore, because the energy is being released, we have a negative enthalpy change. So for any exothermic that's ever going to happen, we will only get a negative enthalpy change. And the reaction profile for this, so the reactants at the top and the products are at the bottom. So looking at the energy, the products have less energy than the reactants. So we have lost energy because the energy has been given out to the surroundings, so the products have less energy. So next we have the endothermic reaction. So this is the opposite of exothermic. So the energy is taken in from the surroundings now to the system. So the energy is not being released this time, it's being taken in. And this happens, for example, when we are breaking bonds this time. So breaking bonds requires energy, so that's the endothermic process, and making bonds releases energy. So the enthalpy change for any endothermic direction would be positive because we require energy. So looking at the reaction profile for this, as you can see, the reactants are there and the products would be there. So the products have more energy than the reactants, as the energy is taken in to make the products. Therefore, the products have more energy than the reactants. Okay, so you need to be aware of the standard conditions. So the standard conditions has this symbol and the conditions for it. So the temperature is always 298 kelvins. So that would be equal to 25 degrees. So remember that when we're converting from Celsius to kelvins, we add a 273 to it. So 25 plus 273 is 298. And because most of the reactions that we look at in chemistry, we measure them in kelvins. So you need to know that temperature has 298 kelvins under standard conditions, and it also has a pressure of 100 kilopascals, which is also 1 atmosphere. So these are the standard conditions. So a few definitions that you should be aware of. So the standard enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its elements, where all the reactants and products are in the standard states under standard conditions. So that's the symbol for the enthalpy of formation, the standard enthalpy of formation. So as you can see, the standard conditions and sign is up there, and the F basically stands for formation there. So taking this definition into account, so for example, if the compound we are forming is ammonia, so I have NH3. So ammonia can be formed from nitrogen and hydrogen. So we have nitrogen and hydrogen. So what the standard states means is that because nitrogen and hydrogen are both found in their gaseous states, so we can't have solid or we can't have liquid for any of them. So it has to be gas to be in their standard states. And also when we are balancing this, what you might usually do is turn that into a 2, and the hydrogen can turn into a 3 and nitrogen would stay as it is. But this would be wrong, because remember we are forming 1 mole of a compound. So the NH3 would stay as a 1 molar compound, so we can't add a 2 in front of it. It would just have a, remember that when we don't write anything, it just means there is 1 of that. So we will only have 1 mole of this. What we can do about this is we can say that we will have 1.5 or 1.5 of H2, and for nitrogen we will have a half of nitrogen to make it a 1 mole of NH3. So this is what's meant by the standard enthalpy of formation. And the standard enthalpy of formation for elements will always be 0. And this is because if you think about it, for example, if we want to form carbon from carbon, so carbon forming from carbon, this will not require any energy because we're forming it from their standard states. So if we have solid carbon going into solid carbon, we don't require any energy because we don't require anything to change. So this is why the standard enthalpy of formation for elements will always be 0. So now moving on to the standard enthalpy of combustion. So this is where the enthalpy change, this is the enthalpy change when 1 mole of a substance is burnt in excess oxygen with all reactants and products in their standard states, again under standard conditions. So again, looking at the symbol for it, we still have the standard state symbol, the standard condition symbol, but from the formation we had, it turns into a C now. So we have combustion this time. So when we were doing the standard enthalpy of formation, the product could only have 1 mole. But in this standard enthalpy of combustion, it's the opposite, and the reactant we are reacting can only have 1 mole. So for example, if we have aluminium and we're reacting it with oxygen, well, we know that because aluminium is in group 3 and oxygen is in group 2, so we would have Al2O3 to balance these out. So when we would normally balance this, because we have two aluminium in the aluminium oxide, we would just do 2Al, and the oxygen could be 1.5 basically. But this can't happen in this, and because the reactant we are reacting can only have 1 mole, So the aluminium is not allowed to have any more than 1 mole or any less than 1 mole. It has to be 1 mole. So what we would have to do in this case, we would have to make the aluminium oxide a half mole. So the aluminium can stay as it is, and the oxide would have to turn into 3/2. So in this case, because we cannot have 2 moles of aluminium reacting. Okay, so now I'm going to move on to calorimetry. So you need to know the equation of this. So there are 2 steps involved in this. So first, what we do is we calculate the Q. So Q is basically the heat change. So it's measured in joules. And then we have M, and M is the mass of the reaction mixture. So when we come on to examples later, it's not the mass of the substance we are measuring the enthalpy change for, it's the mass of the actual reaction mixture. It's usually the mass of water. It will become more clear with the examples later on, and that's measured in grams. And then we have the specific heat capacity. This will always be given to you. It's usually 4.18 for water. And then we have the temperature change. So this temperature change You do not need to convert into kelvins because the temperature change, whatever you do, it will have the same value, and I will show that later on. So what we do then, so when we get the heat change, is we can calculate the enthalpy change. So the enthalpy change is measured in kilojoules per mole, as I mentioned earlier. What we do is we divide the heat change we've calculated by the moles. But if you notice in this, the heat change we got from the first equation was measured in joules, but now the enthalpy change we're getting out is measured in kilojoules. So that's why when we get the heat change in the first step, we need to convert the joules into kilojoules by simply just dividing by 1000. So now we'll be looking at some examples. So in the first example, I've been told that in an experiment, 1.45 grams of propanone were burned completely in oxygen. And the heat from this combustion was used to raise the temperature of 100 gram of water from 293.1 Kelvin to 351.2 Kelvin, and the specific heat capacity I've been given is 4.18 for water. So what I do with any calorimetry question is I would write the equation down first. So I would say that Q is equal to mc delta T. So then I can start putting the values in. So the mass, I've been told that I've been given two masses here. So I have the 1.4 gram of propanone and 100 gram of water. So remember, in this example, in any calorimetry question, we only look at the mass of the reaction mixture, and in this reaction mixture we only have water. So it's usually the liquid that would be that the mass would be counted off. So the 1.4 gram of propanone was being burnt. We don't care about that. We only care about the reaction mixture. So the liquids inside the reaction mixture. So everything inside the reaction mixture, not what is outside. Propanone is being burnt, but we don't care about that. So we ignore 1.45 for now. So it's only 100 grams that would be counted as the mass. So the 100 grams times specific heat capacity, which is just 4.18, and the temperature change, I've been given two values. So from 350, so the temperature rose from 293.1 to 351.2. So I would just simply do 351.2 minus 293.1, and I get 58.1. So this is the first step. So I'm writing down my working out, and I just get 24,285.8. So this is in joules, remember. So what I have to do is I will convert that into kilojoules. So I just simply get 24.2858 kilojoules. So I'm not rounding up anything just yet, because I want to make sure that the answer I get at the end is as accurate and reliable as possible. Okay, so now we would write the next equation down. So the enthalpy change is equal to Q divided by N. So we have got Q from the first equation, but we do not have N. So N now is the moles of the substance we are measuring. We're measuring the enthalpy change for. So if we look at the first line, we have 1.45 gram of propanone which was being burnt. So in this example, the thing being burnt is what we want to find the moles of. So we would do N equals 1.45 and divided by, so moles equals mass divided by mR. So I know that so propanone has a mR of 58, so I would do 1.45 divided by 58, which just gets me 0.025. So this is the moles now. So I've got everything I need, so I just sub everything into to the equation, and so I have 24.2858 kilojoules divided by 0.025, and this would just give me the final answer, which would be 971.4. Because I know the temperatures I've been given are 4 significant figures, I will just write the answer down to 4 significant figures, and I know the units will be kilojoules per moles. Now there is one thing that I can lose marks for. So I've been told that the temperature increased from 293 to 351.2. So this makes it an exothermic reaction. And for every exothermic direction, we have enthalpy change being a negative value. So that's why we would have to add a negative sign in front of the enthalpy change. So moving on to the next example. So we've been told a student determined a value for the enthalpy change of a sample of propanone again, which was burnt, and the heat produced was used to warm some water in a copper calorimeter, and the student found that the temperature of 150 grams of water increased by 8 degrees when 4.5 times 10 to the power of minus 3 moles of pure propanone was burnt in air. So I've been asked to calculate the value in kilojoule per moles for the enthalpy change when 1 mole of the propanone is burnt. So again, what I would do is write the Q equals MC delta T. So Q, I'm calculating the energy change. So now M, I've been told that it's 150 grams of water. I can just add that in. 150 times 4.18, which is the specific heat capacity. So now the temperature change. So I've been told that the water increased by 8 degrees Celsius. So what some students do here, they make a mistake by adding 8 to a 273 degrees, which gives them 281 kelvins, which changes the whole answer and makes it incorrect. So what you should keep in mind is, for example, let's say if I had a temperature being increased from 5 degrees to, let's say, 10 degrees. So this is Celsius now. So if this was in Kelvin, I would have a 278 being converted into 283. So when we are calculating the temperature change for both of these, so 10 minus 5 would be 5 degrees Celsius. And if we do 283 minus 278 degrees, it would still be 5 degrees Celsius. So we still have the same temperature change. That's why we do not need to convert the temperature change into Kelvin. So if we've been provided with Celsius, this will be fine. We do not need to convert this into Kelvin. Okay, so now carrying on, so we would have 8 degrees there. So this would just give me Q is equal to 5,016 joules. So now I need to convert that into kilojoules for later on. So 5.016 kilojoules. So now I would write the second equation down. So the enthalpy change is equal to Q divided by the moles. So the moles, I've been told for this that it's 4.5 times 10 to the power of minus 3. So enthalpy change would simply be 5.016 divided by 4.5 times 10 to the power of minus 3. And this would just get me the final answer, which is 1114.7 rounded up. So that's kilojoules per moles to the power of minus 1. Again, because the temperature's been increased this time, we need to add a minus in front of it to indicate that this is a exothermic process, not a endothermic process. Right, so now looking at the hardest example, this is again a calorimetry question, but they try and stretch you, and they have added a table instead of just giving me the values now. So I've been told the alcohol 2-methyl propane propanediol, which has this formula CH3 3COOH, reacts to form esters. We don't care about that. We just need the values in. So a student carried out an experiment on a pure sample of this and determined the enthalpy of combustion. And we have been told that under a beaker of water, which contained 50 centimeter cubed of water, and the spirit burner was ignited and allowed to burn for several. So I've been given the temperature values, so the initial and the final, and also the mass of the spirit burner and alcohol. So again, Q equals mc delta T. So I always do that. So Q equals mass. So now looking at the mass, so we have 50 centimeter cubed. So just remember that when it's water has a density of 1 gram per centimeter cubed. So this just means that 50 centimeter cubed would be just equal to 50 grams. And usually with every other, if they provide you with any other thing, it would usually have the same process, unless it's stated otherwise that it has a different density. But usually it's just you just need to convert the volume into grams, and you can just it would have the same volume, the same mass as the volume. So for this example, it'll just be 50. So 50 times 4.18. So temperature change, I will need to calculate that now. So again, because it's Celsius, it's not Kelvins, it does not matter. So I can just calculate the temperature change. So I would just do 45.4 minus 18.1, and I would just simply get 27.3. So that's the temperature change, and this gets me for my value 5,705.7 joules. So now we need to convert that into kilojoules, so that would be equal to 5.7057 kilojoules. So I'm not rounding that up now because I want to keep my answer as accurate as possible. So enthalpy change is equal to Q divided by N. So again, we have 5.0057 divided by so now we need to convert, we need to find the moles. So for this, we've been told the initial mass and the final mass. So if I find the mass change now, so I would get is so I do 2.8.80 minus 2.8.58, and I just get 0.22 grams. So to find the moles, what I need to do is moles equals mass divided by mR. So we have been given the formula for 2-methyl propanediol earlier, so we can just do 0.2 to find the mR. So the mR is 74, so I get 2.97 times 10 to the power of minus 3, and these are the moles of this. So now I can just calculate the enthalpy change, so I can sub the values in. So 5.7057, 2.97 times 10 to the power of minus 3, and this just gets me the enthalpy change of minus. So remember, because the temperatures increased from 18.1, so it should be minus 1921. So kilojoules per moles, and this is how you would answer the calorimetry questions. So there are a few questions they can ask you in addition. So for example, suggest one improvement that would reduce the errors due to heat loss in the student's experiment. So what you can do is you can reduce the distance between the flame and the beaker. So for example, let's say we have a flame there, so that's my Bunsen burner, and we have a beaker which is hot, but we have another flame, and the beaker is much closer to the flame. So in the beaker that's quite far apart from the flame, there will be heat energy traveling to the beaker, but there will be a lot being lost. So the heat energy can travel to a lot of other places, whereas for the beaker that's quite close, there will be really small amounts of energy that will go into other places. It will be mainly going towards the beaker, so this will minimize the heat loss, as well as adding a lid to keep the heat inside. This will also minimize the heat loss. Another common question in these type of questions is that suggest one other source of error in the student's experiment, excluding heat loss, or apparatus error or student error. So this can be due to incomplete combustion. So we require complete combustion for this, but we might get incomplete combustion instead, which is basically an error. And explain why the experimental value for the heat energy involved in this experiment is less than the correct value. And again, this is because the heat energy is lost to the surroundings, so it's not traveling to the beaker, it's instead going to other places, so we get less heat energy going to the actual beaker, and that's why it's less than the experimental value. Thank you so much for watching this video. If you did like this video, don't forget to subscribe to see more of these, and you can watch my recent videos by clicking on the links popping up. Thank you.